I love this cartoon. It says, "Why is that woman scowling at me? Do I know her?" And it says, "If she loves you more each and every day, by linear regression, she hated you before she met." Might have to explain that. So today we're going to look at the regression, or we're looking at regression with coefficient of variation. So, by the way, the joke is, see, here's the love. It keeps going up. But after a while, it goes backwards and it goes negative, so they hate you. Anyways, we're going to go ahead and take a look at that tedious task data. And this is an example from one of my classes. And the data below shows list 1 is the number of digits, list 2 is the time. Which variable is independent? So you should be able to tell me which variable is independent and which one's dependent. The number of digits, or list 1. Which is dependent? Well, the time depends on the number of digits. Now, what does A represent up here in the output from the calculator? A represents the slope. It also represents the marginal change of the dependent variable, how much the time changes, for each unit change in the independent variable. All right? So in the tedious task example, we can say for every increase of 1 unit in list 1, which is digits, we expect to see an increase, because A is positive, of 0.517 units in time. Now you can also say that as seconds. Do we expect it to be positive or negative based on the graph? Well, since the slope is positive, we expect it to be increasing or positive. Now, what does B represent? Well, that should be the y-intercept. In this case, it's a little bit negative. You can see the lines going down below. So if I write down the least squares regression line, what I want you to do, you can write down y equals 0.517x minus 4.6. It's nicer if you do it in the context of the problem, because we know list 1 is the number of digits and list 2 is time. But the other way you could write this is y equals 0.517x minus 4.6. Now, in our example, our correlation coefficient is this one, and that would be 0.9263. Is that low, moderate, or strong? When we're between 0.8 and 1, from our last set of notes, we learned that that was strong. And since it's positive here, it's positive there. Okay, so a new thing for you is the coefficient of determination, which is this number up here. Some people said, well, what's the r squared for? It's for this. The coefficient of determination is r squared, and it represents the percent of the explained variability, all right? So in the above example, you're going to change this to percent. I moved the decimal over 2 places, so it's 85.8%. Of the variability in times is accounted for in the linear regression model using the number of digits. So the change in the number of digits explains 85% of the change in the time. To determine unexplained variation, so if I want to know just natural variation in times, I would subtract that from 100%. And in this case, for this student, we're seeing 14.2% variation in time in general that's not related to the number of digits. Usually, this is the main number I'm looking for. But if I ever ask for unexplained, which I could, it's basically the complement, or whatever's left of 100%. Now we can use the model to predict other times based on the number of digits. So you're going to write down your equation with both those numbers again. And this time I'm going to do it for 25 digits, so I'll substitute 25. And I get 8.325 seconds. So I expect that if this student was typing in 25 digits on their calculator, it would take them about 8.5 seconds to do so. I can also do it for 1,000 digits. For 1,000 digits, time is 0.517 times digits minus 4.6, put in 1,000, and I get 512.4 seconds, which is about 8.5 minutes. Am I comfortable with my predictions here? I'm pretty comfortable with 25, because where is it in my data set? It's right here, right? If I'm outside of my data set, like even if I'm at 65 or 70, I don't have to be that far outside. Maybe this is getting exponential. You see what I'm saying? Maybe this person is taking longer and longer every time the number of digits is increased. So I'm not so comfortable with my prediction of 512.4 seconds, but I'm pretty comfortable with my 8.5 seconds. Well, we are comfortable with, that's called interpolation, when we are within the original range of data, and we're good with that. Not so much with extrapolation, because those are predictions outside of the range of data.